As we reach the 30th anniversary of the World Wide Web, there is a quiet revolution taking place above our heads as the future of the internet expands out into space, and not just up to the ISS, but to the moon and beyond, and into what will become the interplanetary internet. Now, some might be saying, why do we need an internet in space when there is no one up there? But it's not just for people that this is intended for. Current communications with spacecraft that go out into the solar system beyond can be tortuously slow, not only because of the limitation of radio waves that have to travel at the speed of light, there's nothing much we can do about that, but the signals become so weak that the data rates are literally down to a crawl by the time they get out to the outer planet, and make 1990s dial-up speeds look positively fast. New robotic probes and increasingly sophisticated spacecraft will need to relay back large amounts of data back to Earth and to other spacecraft if they are working together in a space network. Also, at some point, whenever we get people to Mars, they're also going to need high-speed data connections between here and there. Not just for spoken communications, but for the vast amounts of telemetric and video data that the missions will generate. Even though we haven't got a base on the moon yet, the plans for an internet covering the Earth, moon, planets and the space between is already well underway. We've had the internet in space for a while now with a connection to the International Space Station, but for all the technology on board, they didn't have access to things like Twitter until 2010. This may seem odd, but fundamentally it's down to poor connection speeds, with the astronauts rating it as worse than dial-up. Okay for sending email and pictures and calling home, but not much else. The reason for this is that most of the internet now travels around the world over fibre optic cables and allows huge amounts of data to be moved around very quickly and very efficiently. But the ISS definitely isn't wired, and there isn't a planetary Wi-Fi network they could tap into either. But over the last couple of years, SpaceX and other companies, including Facebook, have been taking what they think will be the first steps in rectifying that situation by setting up a planet-wide Wi-Fi network. SpaceX's plan is called Starlink and would use a constellation of over 4,500 small, low-altitude satellites, which it hopes will be in place by 2024. Now, bear in mind that there are only about 1,500 active satellites in orbit now, and about 2,600 inactive ones. So this alone would double the number of satellites, and that's without any others from the likes of Facebook and other companies if SpaceX's initial trials are successful. Now, while this may be the start of the internet in space, extending it out further is where a whole new set of problems start. One issue is the speed of light, be that radio waves or things like laser light, and it's not something we tend to worry about down here on Earth. At just shy of 300,000 kilometers per second, a pulse of light can travel around the Earth over 7 times in 1 second. This allows us to have real-time communications even on the other side of the planet. But as we get further out into space, even the speed of light won't be fast enough to allow for real-time communications much farther than the moon. At 384,000 kilometers, there is a 2.5 second round-trip delay for a radio signal to reach the moon and back, and that's assuming 0 processing latency. This makes things like real-time remote control very difficult, but not impossible from Earth. But get out to the distance of Pluto, like the New Horizons spacecraft, and that round-trip delay is now increased to 9 hours. Whilst the speed of light limits our ability to have real-time communications, it's not the only problem. Because of the huge distances, the radio signals we send, even if we use highly directional antennas, will still spread out and become weaker the farther they go. Radio signals follow the inverse square law, so for each doubling of the distance, you receive only 1/4 of the power. This is not so bad if you have a very large antenna or satellite dish like we do here on Earth, but on spacecraft, its antenna might be just a few meters across and only able to capture a very small amount of the original signal. As the power of a signal reduces, its signal-to-noise ratio worsens to the point where it becomes indistinguishable from a background noise and is lost completely. NASA can currently receive data from Mars at an average distance of 200 million kilometers from Earth at around about 1.5 megabits per second. But from Pluto, which is 7.5 billion kilometers away, that data rate is just 2 kilobits per second, about the same as a dial-up Usenet connection from the early 1980s, if anybody remembers those. At the moment, there are 3 space networks. The original space network was set up in the 1970s for communicating with satellites and spacecraft and uses 10 geostationary satellites and 2 ground stations to provide 100% coverage around the Earth for craft like the ISS and the Hubble Space Telescope. Then there is the Near Earth network with 17 ground-based stations that deals with communications and data with satellites in a variety of orbits up to and including the distance to the Moon. The last and most sensitive telecommunications system is the Deep Space Network, which supports interplanetary missions and has 3 ground stations at equidistant points around the Earth. So no matter what the position of the Earth is in, it still has a constant connection to any spacecraft out to the distance of the farthest ever man-made probe, Voyager 1, currently over 21 billion kilometers away. The trouble with all of these is that there is more demand than there is capacity, and with new missions from SpaceX, NASA, ESA, India and the UAE planned for the 2020s, as well as possible Mars missions, networks like the Deep Space Network will be reaching their limits soon with the relatively slow radio technology we have now, even though they are being constantly upgraded. This is where the first stages of the interplanetary internet are coming in. NASA is already testing a system called Delay or Disruption Tolerant Networking, or DTN, that is designed to overcome the problems of signal delays due to the vast distances, high levels of noise and solar interference, limited energy resources for spacecraft, and even cyber attack. The idea for the DTN is that it makes use of an automatic store and forward data network. This is different to the normal internet connection, where there must be a continuous connection from the source to the destination for the packets of data to be passed from one node to another. In a DTN, the only requirement is that the next node be available, and if it isn't, then the data is stored until the communications can be re-established, which could be in a matter of seconds, minutes or hours later. Once all the data packets have been received by the destination, they can be reassembled into its original form. NASA first tested a DTN in 2008 with the Epoxy spacecraft, some 20 million kilometers away, to act as a Mars data relay, whilst Epoxy itself was on its way to encounter Halley's Comet. This showed that other spacecraft on other missions could be used to relay data instead of using the normal direct communications method. So, whereas a direct connection between Mars and the Earth might allow up to 2 megabits per second, using a DTN through several nodes might allow 50 megabits per second from the Earth to node 1, and then 50 megabits again from node 1 to node 2, and then node 2 to node 3, etc., until the destination is reached. Each node would also be able to boost the signal sent to the next one, thus improving the signal-to-noise ratio and minimizing errors and the need to resend data, which could greatly increase the data throughput as well. Up to now, all long-distance communications use radio transmissions on the Deep Space Network. This uses microwave frequencies in the S-band, 2 GHz, the X-band at 7 GHz, and the Ka band at 34 GHz. Now, whilst these work well, they have a limited data bandwidth, and the signal spreads out the farther it goes. But the future of deep space communications looks like it will be using lasers. NASA has been experimenting with optical lasers to transmit data between the Earth and the ISS using a system called OPALS, Optical Payload for Lasercom Science. Using lasers is the same method as we currently use to transmit data around the internet on Earth, down fiber optic cables. The laser light is pulsed on and off at very high frequencies in the same way, but in the OPALS system, they are then fired up through the atmosphere to an optical receiver on the ISS. Because of the much shorter wavelength of light compared to a microwave radio link, the Opal system can deliver data rates between 10 and 1,000 times that of the current radio systems. Whilst lasers have a much narrower divergence over the same distance compared to radio and much lower error rates, one of the biggest problems is getting it through the Earth's turbulent atmosphere. NASA is working with Boeing for its adaptive optics, which compensates for the atmospheric distortion in real time by using high-speed cameras and mirrors. In one test between the ISS and Earth, a high-definition version of the Apollo 11 moon landing video was beamed up by radio and then back again by laser. It took 12 hours to transfer the video up to the ISS using the current radio uplink system, but just 7 seconds to send it back to Earth by the Opal's laser system. For long-distance transmissions, lasers could also work much better than radio. In 2013, NASA conducted the Lunar Laser Communications Demonstration, or LLCD. Here they beamed a laser to a satellite in orbit around the Moon and then back to Earth. The test broke all current transmission records with a download speed to the Earth of 622 megabytes and an upload speed of 19.44 megabytes per second. That's some 4,800 times faster than the best radio uplink ever used. In 2019, a new set of tests using a near-infrared laser will begin that will help improve data handling, encoding methods and also tracking. Once in space, there is no atmospheric distortion to contend with, but the very narrow spread of a laser beam means that targeting of a spacecraft with a laser millions or billions of kilometers away will have to be very accurate from both ends for it to work correctly. A radio signal sent from Mars using the Ka frequency band will have diverged of a width greater than that of the diameter of the Earth by the time it arrives. A laser, on the other hand, will have diverged just a few hundred kilometers. This also means that less power is required to send the signal, as it isn't spreading out over a large area, and the equipment is smaller and lighter than the equivalent radio system. Future systems combining lasers with DTN networking should allow data transmissions even out to the edge of the solar system to be several orders of magnitude greater than they are now. And for the first Mars colonists, whilst they'll still have a delay time on the average of around about 20 minutes or so, at least they'll be able to tweet their arrival and send a selfie video back to Earth. If you want to be the first to connect up to the interplanetary internet, then our sponsor for this video, Hover, can be the perfect place to get the right domain like interplanetary.tech or firstinspace.com. Hover specialises in domains and has best in-class customer support, complete with all the features you need to set up for planetary exploration. From finding your perfect domain name to setting up your email so you don't need to use a Gmail address. If that isn't enough, you can also get 10% off your first purchase at www.hover.com/CuriousDroid and using our code CuriousDroid.